Hello everyone and welcome back to Flying Through the Helicopter Flying Handbook. In this video, we're going to continue our discussions around Chapter 11, which is all about emergencies. Now, despite the fact that this is Flying Through the Helicopter Flying Handbook, for the most part, the remainder of Chapter 11 aren't the kinds of things that we can actually fly. These are simulating things that are somewhat catastrophic often, and also I did try a couple of my simulated helicopters and I wasn't able to accurately depict some of the conditions that I'm going to talk about in this video. Okay, so the first thing we're going to talk about is retreating blade stall. So what's that all about? As you already know, the retreating blade is getting a lower airspeed of airflow over it than the advancing blade. So of course, when that happens, what happens is that the retreating blade flaps downward, and that increases the angle of attack. The advancing blade flaps upward, which decreases the angle of attack, and that's how we get balance. However, if we go too fast, we can get retreating blade stall. And this is one of those factors that comes into play when we are looking at VNE, never exceed speed, for our helicopter. This is a limiting factor in that never exceed speed. And of course, if you look at a typical helicopter, that VNE actually decreases as you go up and the air gets thinner. So what happens if you're approaching the situation? Well, you'll tell that you're approaching this bad situation when you're going to have a low frequency vibration. Then you're going to have a pitching up of the nose and then a roll in the direction of the retreating blade. Okay, so remember, in general, if you have low frequency vibrations, those are most likely related to the main rotor, because it turns at a slower speed than the tail rotor and the engine. So why does it pitch up? Well, remember that thing called gyroscopic precession. So once you have a decrease in lift on the retreating blade side, that is felt 90 degrees later. So instead of being felt on your left in a standard helicopter, that is felt at the rear. So the rear of the rotor disc wants to drop. That causes the nose to pitch up. So that's the initial tendency. Well, then you have a loss of lift on the left side, and that loss of lift causes it to roll in the direction of the retreating blade. And there you have it. So how do you recover from this? Well, there's a couple of ways you can recover from this. You could slow down. However, you have to be careful. If you slow down and you're already in it, by pulling back on the cyclic, you might just make the situation worse. One way you can make it a little bit better is to reduce the collective a little bit, but you want to not go too crazy because you might be at the ground. Right? So if you're at the ground when this happens, then it's going to be kind of a bad situation. So that is retreating blade stall. The next condition that's discussed is ground resonance. So ground resonance is something that will happen with a fully articulated system. So as we know, there are lead lag hinges in that rotor system, and those allow for things to find the balance, if you will. So, in a steady state situation, all of those rotors are a constant angle from each other. So if it's a 3-bladed system, say in a Schweitzer, you're going to have 120 degrees between the blades. But if I have a sharp blow, as depicted here, where I hit the ground hard, maybe on a skid, or if I have wheels, as in this picture, on a wheel, it can jar those things out of place. And once that happens, it's like having a unbalanced washing machine. And this thing is just going to wobble, and it can get worse and worse and worse. And if you look online, you'll find some videos of helicopters blowing themselves apart. What do? You have a couple of options. If you have enough RPMs to get off the ground, if you're not on the ground, you can't have ground resonance. Makes sense. So if you have the RPMs, you can pick back up, and very quickly this will rebalance itself. If, however, you don't have enough RPMs, you want to drop the collective and chop the throttle and hope for the best. Now, in some helicopters, this actually seems to work pretty well. For example, in the Schweitzers, this works rather well, and it will almost immediately stop a ground resonance. Now, I've actually experienced this a couple of times. If you're doing, let's say you're doing a slope landing and you don't go slow, this can happen. But that's not really where I've seen it the most. Where I've seen it the most is actually people doing run-on landings where they don't resist the urge to drop the collective as soon as they make ground contact, and then the skids grab, and then it jars those rotors out of place. Next thing they talk about is dynamic rollover. So you already know that a helicopter can roll over if the CG is over a pivot point. So here they have a picture of a helicopter where it's hitting the right skid. That becomes a pivot point. So if I'm coming in on a slope, I can certainly catch a skid and create the pivot. Or if I'm even coming in on a flat surface and I get a skid caught on something, like maybe it's stuck in mud or some tar, whatever, that can also cause the situation. So once you get to the situation where the CG is on the wrong side of this pivot point, if you will, then you're pretty much going over. Now, that's what I've just described as essentially static rollover. But if I have a good momentum, if I'm coming sideways, in this case to the right, I might have enough momentum when I hit the ground and this becomes a pivot point to roll over my helicopter. So, what do we want to do? If we're coming in and we're doing a slope landing, we want to go slow, slow, slow. That's what I always tell my students. Other things they'll talk about is how can you avoid these issues. You want to practice your hover autos into the wind. And also don't do it when the winds are really strong and gusty either. Other precautions we can take is do a 2-step liftoff. Don't just yank it into the air. Again, if you're doing a slope, especially. Remember, where's your wind? If the wind is coming from the upslope direction, there's less lateral cyclic available to you. Avoid tailwinds, especially with slopes. Remember that less lateral cyclic control is available due to translating tendency of the tail rotor when the left skid or landing wheel, as appropriate, is upslope. So that's one reason why if I'm flying something like a Schweitzer, I always try to have right skid upslope. I've flown with some pilots that say, oh, I want to have the skid below me upslope, whatever skid that is. That's not correct. You want to have the right skid upslope, if you can, in the case of a standard helicopter. And keep in mind that the lateral cyclic requirements change if you load or unload passengers and cargo. Also be aware that if the helicopter utilizes interconnecting fuel lines that allow fuel to automatically transfer from one side to the other, you've got gravity. And gravity is going to cause the fuel to flow downslope. And that might cause a CG change, if you have a significant slope. Now, reality is, if you have a significant slope, you probably can't land on it anyway. But it is something to keep in mind. And some other situations. Don't allow the cyclic limits to be reached, right? If you're landing on that slope and you hit that limit, bail. Get out of there. It's not going to allow you to provide any more input. And in the case of some rotor systems, it could also lead to mast bumping. During your takeoff from a slope, begin by leveling the main rotor disc and then, and only then, go out to the side. You don't want to slip down the hill, and you basically want to raise the downslope skid and make sure everything looks good, and then you can get away. And finally, be aware that dynamic rollover can be experienced during flight operations on a floating platform if it's pitching and rolling. So if you're trying to land on a barge or a ship or anything that's floating, you want to look at what's going on. So that is dynamic rollover. Okay, other conditions. And if you're flying a Robinson, you really need to know about this. Low G conditions and mast bumping. So if you have a two-rotor system, a semi-rigid system like you would find in the Robinsons, you have to be careful about low G maneuvers. And what can happen if you have low Gs? A couple of things will happen. One thing you can get is called mast bumping. And what is that? What happens is the rotor is allowed to teeter until the static stop, or the ground stop, if you will, contacts the rotor mast. So how will you know if this is happening? You might hear a very loud thumping noise. It'll sound like someone is taking a sledgehammer to your rotor mast. You're probably only going to hear that a couple of times, and then you're going to not have a rotor mast anymore. That thing's going to snap off, and you will be contemplating life or however long it takes you to plummet to the ground. And there's not a lot you can do about it at that point. So that's mast bumping. Now, how do we avoid things like that? So in a rotor system like in the Robinson, here's what can happen. If you do a low G pushover, let's say you're climbing and maybe you're an airplane pilot and you go back to what you first learned. It's what we call the law of primacy. You push over and suddenly that rotor system gets unloaded. So normally that rotor system is kind of hanging and exerting pressure on the teetering hinge. All of a sudden that pressure is released and that rotor is just able to flop around. Right? There's nothing weighing it down, if you will. Also, it was coned upward, and now it's not coned at all, and possibly even it can cone downward. Right? There's kind of a springiness to those rotors. So you can essentially snap it from coned up to coned down. Now, all of these things are bad. So what can happen? You can get mast bumping. The other thing you can have happen in those Robinsons is it uncones or it cones downward, however you want to say that, and you can lose your tail rotor mast. More than one Robinson has had its tail cut off from this condition. So how do you avoid this? If you get into any kind of turbulence, reduce power, cruise slower, when in doubt, pull back on the cyclic. That's going to load up the rotors and slow you down. Both of those are good things in this situation. Don't be so quick to push forward. Can you push forward on the cyclic? Of course you can, but you want to do it slowly and smoothly. I think if you ever learn to fly a gyroplane, if you're a Robinson pilot, you'd probably be one of the better ones, because gyroplanes also, you don't want to shove forward on the cyclic. That leads to bad things in those as well. So that's mast bumping and low G's. Other things, low rotor RPM and rotor stall. Your rotors aren't spinning fast enough. It can lead to the retreating blade stalling, and we talked about what kinds of things happen when that occurs. Again, in the case of something like the Robinson, you might think, well, this is not an issue for me because I have a governor, so I don't have to worry about the rotor RPM. Yes, you do. Because if you just keep pulling up on a collective, that rotor RPM will drop once you get to full throttle and you keep pulling. So you have to pay attention to what's happening. You can get low rotor RPM from that. The other thing, of course, that can cause the low rotor RPM in something like the Robinson, if you don't recover or react immediately when you have an engine failure and the rotors spin down. If they spin down below 80% plus 1% per 1,000 feet or so, you will never, ever get those rotors to spin back up again. So if you're flying along, it doesn't matter which helicopter it is, and you have low rotor RPM, what can you do? Well, I like to say lower roller. Lower the collective and verify or roll on full throttle. So roll up the throttle. The rest of this chapter talks about things like system malfunctions. So what do you do if you have an anti-torque system failure? Well, it depends. What exactly happened? Let's say you're in cruise and this happens. A lot of helicopters, if you fly forward at a certain speed, the stabilizers on the helicopter will keep you from spinning. Other things that people will say, you might hear this phrase, when in doubt, auto out. If you're in an auto rotation, there is no torque. So you might be able to control the yawing motion or the spinning, if you will, if you enter an auto rotation. Now, if you're landing with a stuck pedal, then you might want to consider something like a run-on landing. Again, if you have a little bit of forward speed, that might help you. So if you are doing something like this, maybe you can't get rid of all the yaw. If you definitely can't get rid of all the yaw, land it level. I'll say that much. You don't want something to just grab unevenly as you're spinning on the ground. I was just recently, I saw someone doing a auto rotation online. They published their auto rotation in an MD-500, and they were really proud of it. However, if you looked at the video, it was pretty clear that they landed on the heels of the skids. And you can see from the video that what happens when you do that is it slams down the nose, which is something we've talked about in previous videos. Loss of tail rotor effectiveness. This is something you learned way back when we talked about aerodynamics. We do not like winds from the left in general in a standard helicopter. And there are 3 things that will cause a loss of tail rotor effectiveness. So this is the kind of thing that we worry about on those windy days. So the first one here is main rotor disc interference. I have a wind coming from the left. What happens is that here, kind of toward the tip, my vortices off of the tips are going to get blown right back into my tail rotor. So that's one way I can get LTE. Another way is what we call weathercocking stability. So if I have things coming from the back, all those stabilizers we were just talking about can cause the helicopter to try to weather vane or whip around 180 degrees. That's called weathercocking. And then finally, we can get tail rotor vortex ring state. We said, what is vortex ring state? Vortex ring state is when you're descending into your own turbulent wake, and you're essentially doing that. Your turbulence from the tail rotor is getting blown back into it because you have a strong wind from the left. So when you have strong winds in your helicopter, you can always have the possibility of LTE. You have some other failures, like what if your drive shaft fails or your clutch fails? Again, I'll say it again. When in doubt, auto out. What if your hydraulics fail? Well, if your hydraulics fail, normally you're going to have some sort of a backup system. So there's that. So it's going to be hard, but you can still move the controls. What if your governor fails? Well, guess what? Then fly it like you don't have a governor. It's that simple. The Robinsons didn't initially have the governors, but the FAA pretty much said, hey, you can barely fly this thing at all. So why don't you put a governor on it? And they did. Made it a little bit easier to fly an R-22. Vibrations, again, if it's low frequency sounds like the main rotor disc. What if it's higher frequencies? Then you're looking at engine or tail rotor. And then finally, what if you're in a multi-engine helicopter? You can have a single engine failure. If you're flying something like a Black Hawk, that thing has so much power, even with one engine functioning, it's not really going to be a big deal. If both of them fail, guess what? You're doing an auto rotation. Okay, and with that, we have come to the end of chapter 11. I hope you're enjoying this video series, and I look forward to seeing you in the next one.